Welcome to SCP 105, Week 9. We're going to be discussing stars. Stars are, of course, the hosts for the planets that we're interested in, planets that may hold life. But in order to discover these planets around other stars, we need to understand the different kinds of stars that are out there. And so that's what we'll be looking at today. What the nature of stars are, how we know what different kinds of stars are, and how we can come up with a nice and complete explanation of all the different possibilities for stars out in our universe. So here we have a view of many different stars. And in this view, you'll see some stars that appear reddish and some that appear bluish. You'll see some that are bright and some that are dim. For as long as people have been looking up at the sky, we've been able to notice these different features and characteristics of stars, their different colors and their different brightnesses. But for a long time, we didn't really know why stars had different colors. We also didn't know why they had different brightnesses. And it took some time before we discovered the explanation. We're going to be basing most of our understanding of stars on our understanding of our own star, the sun. We actually know quite a bit about the sun since it is so close to us. We know about the many layers of the sun by doing some interesting observations of it. And we also have come to understand that the sun is a fairly average star. It's a normal star out there in the universe. But what about all the others that we see from night to night? Well, of course, there have been many people that have studied these stars over the course of history, but perhaps none were as productive and as influential as the women you see in this picture. These are the so-called Harvard computers. They worked at Harvard College Observatory in the 19th century. And their job was to take photographic plates and examine them very carefully and collect and organize the data about all the stars that were on these photographic plates. Photography had been recently invented. Before then, all the observations of stars were done with human eyes, and if you were lucky, with telescopes. But if you attached a camera to the back of a telescope, you could get lots of information to examine later on. And that's what these women were doing. The story of why women were working in this field is one that's deeply related to the sexism that was part of the academic environment at the time. At the time, Harvard College was all men. All the professors, all the students, everybody was male. And the Harvard astronomers were interested in getting lots of data, but didn't want to do the work of organizing it and carefully observing, making the measurements. And so they wanted to hire people to do that work. And the cheapest labor at the time was women. But because the women were working with the data, they were the ones that ended up making the discoveries. And in this picture, there's at least 3 different women who went on to get their PhDs in astronomy. The first woman to get a PhD in astronomy was the first woman to get a PhD from Harvard. And also the first woman to be a professor at Harvard is in this image as well. She's actually in the front, Annie Jump Cannon. Amazing discoveries were made by all of these women. And we're going to go through and actually use their discoveries to explain many things that we now know about stars. So what are the things we can measure of stars? We can measure only about 5 different properties of any given star. We can measure how bright the star is, what color it has. We can measure something called parallax, which will tell us about how far away the star is. We can measure the variability of stars. That is it getting brighter and dimmer over time? We can also measure the spectrum of a star. In other words, we can take the light and break it into its wavelengths and see how much light is coming out at different wavelengths. We'll look at each of these in turn and find out what that tells us about these stars. And these were the various things that the Harvard computers were looking at as well. So first, brightness. What do we mean when we say brightness? Well, there are 2 things that can affect the brightness of stars. One is that stars could just give off more light or less light, making them brighter or dimmer. Call that the intrinsic luminosity of a star. And here's an example of what that might look like. Some stars give off a lot more light because they're bigger. Some stars give off a lot more light because the surface of the star is glowing brighter than other stars. And you can see both of those effects in this artist's impression of different sized stars compared to each other, different colors and different brightnesses. When you look at a star, of course, you can't tell how big the star is just by looking at it. We only see a point of light. So to figure out how big the star is requires a little bit of cleverness. We'll describe in a bit what that cleverness is. But there's a problem. We don't know whether the stars are bright because they're intrinsically bright, intrinsically luminous, or whether they're bright because they're close to us. We need to figure out how far away a star is before we can figure out what is the nature of that star. And that's the effect that distance can have on brightness. We've already looked at what the effect distance has on the amount of light we receive. And that effect is something called an inverse square law. You've worked a little bit with that already, but the idea is that when we look at a star and we see that it is dimmer than another star, and we suspect that both of the stars are giving off the same amount of light, the difference in the brightness has to be how far away the star is. If one star is a quarter as bright as another star, that means that the star that's a factor of 4 dimmer would be twice as far away. If we see another star that's 100 times dimmer than its counterpart star, and we have reason to believe that their intrinsic brightness is the same, then the star that's 100 times dimmer will be 10 times further away than the other star. And it's through this sort of calculation that allows us to compare the different stars. And if we know the distances between 2 stars, we can actually tell what the intrinsic brightness is and get at some of the better questions of how much light stars are actually giving off intrinsically, how bright they might be, and why they're producing the light they are. This brings us to the next character of stars, which we start to understand, which is the color of stars. Now, we've already discussed where the color of stars comes from. It comes from the temperature that stars have. As you heat any object up to hotter and hotter temperatures in excess of thousands of Kelvin, then those objects will glow, starting with red, going all the way up to white hot, and then even beyond to blue hot. Here's a nice chart that actually shows what those different temperatures are in Kelvin. This is a chart that's used by painters and by lighters to think about what sort of light people would want in a room. The temperature that's given is indicating a certain color of light, but it's also indicating what colors would be produced if you heated up any object to that temperature. Then stars follow along in this scale. So we go from the coolest stars, round about 1800 Kelvin being very red, to the hottest stars, up at around 10,000 Kelvin, being very blue. Color and brightness are related. Blue stars are giving off more light because they are at higher temperatures than red stars. And that's an important observation as well. That's going to allow us to come up with some other understanding of how stars behave. But the next thing that we'll look at for stars is their parallax. Parallax is an interesting effect. It's an effect that the star appears to move compared to background stars over the course of a year if it's close by. You can see why that is from this diagram. That movement is very small. Sometimes it's so small that it's hard to perceive it as dramatically as you can see in this diagram. But if you can make this measurement, you can actually get a distance to the star, which is an important thing to know if you want to disentangle all of these other characteristics. It is, in fact, from this measurement that we get the measurement of distance called the parsec. A parsec is the measurement of a distance to a star when that angle, that change in the view, is an angle of 1 arc second. That's 3,600th of a degree. Very, very tiny motion in the sky. But with a good enough telescope, you can actually measure that and figure out when stars are farther away or closer by, just by looking at this parallax effect. Another aspect that the people observing stars can look at is their variability. And in fact, here is a plot of variability that the Harvard computers were looking at in 1889. It's on the back wall. The star they were looking at was Beta Auriga, which is a fairly famous variable star, getting brighter and dimmer over the course of a month. That variability is something we're going to look at very closely, because the variability in stars that we will observe will actually tell us that there are planets around them. And that's going to be the key measurement and focus for us for figuring out that stars have planets. Finally, one final thing you could look at a star is the spectrum of a star. You can look and see what the different wavelengths of light are being produced by that. One way to think of this is by taking the light from an object, let's say the sun, and passing it through a prism. You'll see a rainbow, which is really just a way of breaking down the amount of light coming at different wavelengths from the red to the blue. You could do this for any star. And then when you do that for other stars, you get very interesting information about the particular kinds of light coming from stars. And this can also give you information about the atoms that are in stars. And one more piece of information, which is how quickly the stars are moving. This is an example of what the spectra of stars looks like. Now, these spectra, you can see, often have similar features. First of all, you can see the rainbow colors from red to blue, all the way to violet at one end. Some stars have more red light, some stars have more blue light, and that corresponds directly to the color of the star. So if you see a spectrum that has very little red and a lot of blue by comparison, you can tell that that's going to be a bluer star in the sky. Contrary-wise, if you see a spectrum that has a lot of red and not a lot of blue, that'll be a redder star. The stars are arranged from the very top down to the one that's above the bottom three in order of color, so that the top one is colored blue and the bottom one is colored red. And if we were to collapse those spectra down, you would actually be able to see that this was a progression of color and therefore progression of temperature, with the O stars being at temperatures at about 10,000 Kelvin, and the M stars at the bottom being a temperature of about 2,000 Kelvin. Now you'll notice that there are letters and numbers that are given on the left-hand side for all the different stars. On the right-hand side, we have the names of the stars. Usually these are the catalogs and the numbers. But on the left-hand side, we have something we call the spectral type, which are given as letters. And the letter ordering happens to be a mistake of history. When the Harvard computers first started looking at the spectra of stars, they organized them as A, B, C, D, E, and so forth. It was only later when we organized it by temperature that we realized that some letters didn't really show up in the sequence, while other letters were sort of out of order in terms of temperature. And so the temperature order from hottest to coldest is O, B, A, F, G, K, M, as you can see. And those will be referred to from time to time. Our own star, the sun, is a G star, right in the middle. Really hot stars might be called OB stars. The coldest stars are M stars. They happen to be quite small. They call them M dwarfs. And if they happen to be much larger, they call them M giants. There's also a few other kind of weird stars shown here. There's an F metal poor star. That's a star that is of spectral type F, but that doesn't have a lot of the atoms other than hydrogen in its spectrum. In astronomy, we call anything other than hydrogen a metal, which is a little confusing because that's not how most other people describe metals, but that's what we say in astronomy. There are some stars that are giving off light at certain wavelengths more intensely. We call those emission stars. We have an M emission and a B emission star shown here. And you can see that there's bright lines that show up where there are dark lines for other stars. Those dark lines are indications of atoms. The darkest lines you see in the B and the A stars and even into the F stars, those are hydrogen lines. Those are indicating that hydrogen is in those stars. You might see a really dark line in the yellow part of the spectrum. That's a very famous line called the sodium line. And then in the blue part of the spectrum, you might see a few lines that show up that are associated with calcium. And there's a lot of other lines as well that are associated with other atoms. This is how we ended up figuring out what stars were made out of. There are some very intense lines that you can see, but there's also very faint ones. And measuring those actually shows all the different elements that show up in stars. And if you're very careful with your calculations, you can even tell how much of each element there is. In fact, it was a student of Harvard computers, her name was Celia Payne-Gaposchkin, who came up with the first calculations that determined that stars were made out of mostly hydrogen and a little bit of helium and not much else. Everything else was sort of on the realm of 1% to 2% at most. Amazing discovery that she made, but this was something that you needed to look at the spectrum of stars to figure out. So that's the spectrum of stars. And as we begin to evaluate all this, we can find out two different things about any star once we use all of this information. One thing we can find out is how much light the star is giving off. We call that the intrinsic luminosity. We figure that out by knowing how far away the star is, and then using our understanding of the rules for how things get dim as they get further away to figure out the intrinsic luminosity of stars. And then we take that spectral type and rearrange it by temperature and put those two things together to form a diagram. This diagram is very famous. It's called a Hertzsprung-Russell diagram after the two astronomers that first published it in the journals. But it's so famous now that we often just abbreviate it HR diagram. Or sometimes people just describe it as a color magnitude diagram, color being associated with the spectral type and magnitude being something that's associated with the intrinsic luminosity of stars. When we look at these two features, we see a pretty amazing trend for all the stars. And this is the trend that we see. So this is a mock-up of this diagram. when you make this diagram, you do have to measure individual stars, and you measure how much light they're giving off. And you also measure what color they have or their temperature. And each star that you find, you put a little dot on the diagram, making it a scatter plot. Now, if you can find thousands of stars, or even millions of stars, that will fill out this diagram beautifully. As it is, it's a little hard for us to show individual stars then. So what you can kind of see from this diagram is there are kind of clouds and trends and perhaps some sequences of stars that seem to appear. And then there are some places in the diagram where there don't seem to be very many stars at all. In those places where there's a lot of stars collected, we seem to want to explain that. And so we explain that as different kinds of stars. So let's first talk about what the different axes of this plot are. The one that's vertical, going up and down on the side, is telling us how much light is given off by stars. It's the luminosity of every star. So if I know how much intrinsic luminosity a star is giving off, I can place it somewhere along that vertical axis. And you can see it goes from 10 to the -5 all the way up to 10 to the 6. In other words, 100,000 times dimmer than our sun at the bottom, up to 1,000,000 times brighter than our sun at the top. And remember, this is intrinsic brightness. So this is the amount of light that the star is giving off where it's located. If you imagine what it would be like to have a star that would be 1,000,000 times brighter than our sun, located at the distance of our sun, we would absolutely cook. On the other hand, if you had a star that was 100,000 times dimmer than our sun, we would freeze. So that's an interesting thing to consider when we're thinking about planets around stars. But there's a wide range of possibilities for luminosity. And depending on what the luminosity of the star is, the location of the planet will have to be different if it's going to be in the realm of the temperature we're interested in, maybe the temperature that allows for liquid water. So the main group of stars in this diagram runs from the top left to the bottom right. And along the bottom, you can actually see the sequence of temperatures, starting at the hot temperatures on the left, in excess of 30,000 Kelvin, going to the coldest temperatures on the right, down to almost 2,000 Kelvin. You can also see the spectral names, OBAFGKM, taking the locations where they are. So that means that that main sequence of stars, where 90% of the stars in our universe will lie, if you put them on this plot, which runs from the top left to the bottom right, is a sequence both in amount of light being given off, but also a sequence in color and temperature. And you can kind of say some interesting things about this. Because the star is giving off more light, that generally means that it has to be a little bit bigger in order for it to give out the enormous amount of more light that we see. The calculations indicate that stars that are in the upper left are much larger stars than our sun in terms of size. And when we talk about size, we talk about the radius of stars. And the calculations show that there are lines of constant radius that run from the left to the right, kind of in a diagonal fashion. And you can see them listed there, all the way down to 1,000th of a solar radius, which is smaller than the Earth, up to lines that run 1,000 times the size of the sun, which is about the orbit of Mars. So we have a huge range of sizes for stars too. And anywhere those lines intersect a star that's on this diagram, that's telling you how big the star is. So now we know the size of stars just by looking at this diagram. So we get a lot of information. If you see a star on this diagram, you know already how much light it's giving off, what color it is, what temperature it is, and what size it has. Another amazing thing that you can do is, because we know stars are powered by nuclear fusion, we know that there has to be a certain amount of material in the star in order for it to produce the light that it produces. That means there's a relationship between how much stuff is in the star and how much light it's giving off. The stars that are shining because of nuclear fusion are in that 90% swath, the main sequence. And so it's on that sequence that we can actually say what the masses of stars were. This was first observed directly, where they were able to see what the masses of stars were by using some rules from gravity. But now we can actually calculate it theoretically, because we know enough about nuclear fusion and how stars work, to allow us to say with certainty what the masses of stars are when they're along that main sequence. And you can see them indicated starting at about 1/10 the mass of the sun in the M stars in the main sequence, going up to 30 times the mass of the sun in the hottest and brightest and largest O stars. So the main sequence is a sequence in size, it's a sequence in mass, it's a sequence in color, it's a sequence in temperature, and it's a sequence in the amount of light that's given off. And because of this, we often give names to different parts of that sequence. For example, down in the lower right, we call that area the red dwarfs. They're red stars and they're small. Whereas on the upper left, we call that area the blue giants, or even the blue supergiants if you get up to the highest parts of the diagram. But those aren't the only places you see stars on the diagram. You also see stars that seem to jut off right about the location of the sun. They jut off to the upper right, becoming redder and redder and bigger and bigger. Those are giant stars, as you can see, because they intersect sizes that are 10 times up to 100 times the radius of the sun. But they are in the main sequence, so we don't have a lot of information about what their masses are. Because in fact, these giant stars are still being powered by nuclear fusion, but it's not the same kind of nuclear fusion. What has happened is they've used up all of the fuel at the center. Material have collapsed back down, and that's restarted other fusion processes, which causes the star to actually expand and become brighter, but also cooler. Those are called red giant stars. So most of the stars that are on this diagram are going to be stars that are like our sun or cooler. And at the point where they run out of fuel, they all become these red giants. About 10% of the stars we see in the sky fall in that part of the diagram. There are a smattering of stars which are supergiants. Some of these are red giants that have kind of gone through many processes and have really expanded and are just at the end of their lives. Some of these are blue giants and blue supergiants that are also kind of running out of fuel. What happens when the star completely runs out of fuel? Well, a couple things can occur. If a star is big enough, if it runs out of fuel, it can actually collapse and have a catastrophic explosion called a supernova. Those are only for the very largest stars. But stars like our sun and most of the red giant stars, the outer layers will actually become unbound from the core of the star, and they will start to move away as the winds push them off. And you'll be left with just a core that doesn't have any nuclear fusion, but is very hot because it's collapsed down to a very small size, a size that's about 100th the size of our own sun. So what happens is there's a transition as giants actually flip from the upper right side of this diagram down to the lower left, and you can see there's an entire sequence of dwarfs. This is the stellar graveyard. These are the stars that are left over after the giants have gotten rid of their outer layers. White dwarf stars are much, much smaller than the main sequence. Again, we don't know much about their masses, although I can tell you that their masses are under about 1.5 solar masses. There's actually a famous calculation that was done by Subrahmanyan Chandrasekhar, a famous astrophysicist from about 100 years ago, who calculated what the maximum size of some of these leftover remnants could be. Now, some of them are much smaller in mass as well, but all of them are so small that they're basically the size of Earth in terms of the amount of space they take up. But of course, they have a lot more mass. You can think of them as glowing embers, and they're a little bit hotter than the stars that they came from because it's the core that's left over. And they're slowly cooling off. These are the white dwarf stars. The last thing that's interesting on this diagram are the green indicators, which are telling us how long stars will live. That is, how long will stars stay on the main sequence, burning the hydrogen at the core, which is the way that most stars get their power. Our own sun, you can see, has a lifetime of about 10 billion years. We're about halfway through. After 10 billion years, it'll turn into a red giant, swallow the Earth, and then eventually turn into a white dwarf. Stars that are more massive than the sun, interestingly enough, don't live quite as long. And it's a little bit confusing until you understand that they're actually giving off so much more energy. Their luminosity is so much larger that they're running out of fuel more quickly. Even though they have more fuel to begin with, the amount that they're actually using is so much greater that their lifetimes become shorter. So you can see as you move to other spectral types on the main sequence, let's say I move to the B stars or the A stars, lifetimes go down to 1 billion years, or 100 million years, or even 10 million years up at the O stars. Now, 10 million years sounds like a long time, but for life, it's actually not that long. 10 million years is not that far back in our past if we think about the history of the Earth. Even 1 billion years isn't that far back into our past in comparison to the age of our Earth. And if you think about how long it took life to emerge on our planet over the course of billions of years, having a star that only survived for 100 million years before it became a giant and swallowed up any of the planets that were around it or exploded in a supernova might give you pause as to whether the more massive stars could host life as we know it. It is possible that it's the very lifetime of stars themselves which determine whether life can show up on the planets that are around them. Of course, we have only one example we can point to, but that's definitely something that people have thought about. Could it be possible for a star like Sirius, which seems to have a lifetime of about 1 billion years, to have a planet that has life around it? Perhaps, but if you think about how long it took for human beings to show up on planet Earth, some 4.5 billion years, at that amount of time, Sirius will be gone. There won't be such a star any longer. And that might mean that if we're interested in things like intelligent life, and if we think that we're a good example of that, well, then you might need to wait longer than you have star lifetimes for the hotter, bigger, and larger stars on the main sequence. Most of the stars on the main sequence are the stars that are less massive than the sun. 90% of the stars in the main sequence are M dwarfs. And those stars live much longer than our own sun. In fact, most of those stars are just starting out in their lives. They are still babies, as it were. And well after our own sun is gone, they will still be shining brightly. some for 100 million, 100 billion years, some for even a trillion years by certain calculations. And so the thought has occurred to others that although maybe life is around stars like our sun, if life forms around M dwarfs, well, it might have a chance to survive for trillions of years, much longer than life has survived here on Earth. Very interesting things to consider. But I'd like to take a moment to think about some of the other aspects of stars, just so that you have a good understanding of them for when you're considering which stars might host planets with life. You might recall that I said that if you did this with real data, you'd see lots and lots of points kind of shown everywhere. And this is showing you just that. You can see the main sequence running down here, and the red giants and a few supergiants, and maybe even some white dwarfs in this data. This is rather old data now. There's much newer data available that shows the same thing. And here we see the process that takes hydrogen and turns it into helium, powering most stars that are on the main sequence are powered in this fashion. This is a diagram that shows the center of our own sun, that shows how the core of our sun is producing the energy. That energy takes a very long time to reach out to the surface and heat it to the temperature, which is about 5,700 Kelvin or so. As scientists study stars, they begin to get interested in how they change from a main sequence star into a white dwarf. This is one process that happens, and this diagram is still the HR diagram, just without the colors and the names of the stars on it. And as you follow this path, this actually shows what happens at the end of the lifetime of a main sequence star. That's a little bit more massive than our own sun, all the way down to a white dwarf. When I talk about a lot of these stars, it's nice to hear some examples and see them. So here's an example right here. This is a red giant star. This is the star Betelgeuse. This is one of the stars in the constellation Orion. And if you can find it in the night sky, you'll see that it is actually very, very red. It's also a red giant star. And I told you before that most stars are just points of light, but this is a big enough star and close enough to us that using the Hubble Space Telescope, you can actually resolve the size of the star, which is very difficult to do for other stars. This is an observation of a white dwarf, the first one ever discovered. It's actually a star that orbits the brightest star in the sky, Sirius. Sirius A, the brightest star in the sky, is an A-type star, very bright, very blue. And as we said before, it'll have a lifetime of about 1 billion years. Well, it turns out that it has a companion star. The companion star is much fainter than it. But if you look at that companion star in X-rays, you find out that that companion star is actually very bright in X-rays compared to Sirius A. The reason for this is that Sirius B is actually hotter than Sirius A. It's giving off more X-rays because it has a higher temperature. That's pretty remarkable. This is one of the sort of interesting things of white dwarf stars. They can be much hotter than the other stars, even a star that is much brighter, giving off much more light than it. It's because they're very tiny in size, but very hot and very blue in color. The formation of white dwarfs, of course, happens when the outer layers of a red giant leave. This is an example of that occurring. This is the so-called planetary nebula. When those outer layers do leave, they can travel for quite some distance. They make for beautiful images in the sky. Some of the most beautiful pictures that are taken of planetary nebula. Here's another example. of a planetary nebula, a star at the end of its life. And at the center, you see a young, newly formed white dwarf. What's interesting about the white dwarf is that it has a temperature that's probably 100,000 Kelvin, which is hot enough that even though it's a very small star, it will have temperatures at about the distance between it and the Earth of a 1 AU that could be as hot or even hotter than the temperature we have here on Earth, just because it's such a very hot ember that's left at the end of the life of the star. So here we see the life cycle of our sun for comparison. Right now we're at about 4.5 billion years. After about 10 billion years, eventually the sun will form into this red giant, perhaps this planetary nebula, and then on to a white dwarf forever and ever after. But what ends up occurring at the center of the star is more and more material is produced in stellar nucleosynthesis, a topic we talked about before. For very massive stars, you can actually make a lot of different nuclei at the center. This is the most massive star that you can have, some star that's probably about larger than 8 times the mass of our own sun. And when that occurs, you get these layers of different nuclei forming at the centers until you get to iron. And when you hit iron, then there's no more fusion that's possible. And so the entire star collapses and explodes in a supernova. On the right, you see the original star of a supernova that happened in a nearby galaxy. And on the left, you see what happens when it explodes. It outshines all the other stars in the galaxy. An incredible destructive explosion, but as we've seen before, creates some of the most important elements for our understanding of the universe and for life. This is what that explosion looks like today, 30 years after it happened. Sort of an amazing kind of shockwave going out through space. Here's another example of a much older explosion, one that happened 1,000 years ago. Shockwave going out through space. And when you look at the center of these explosions, this is one that's also about 1,000 years old, you can see some interesting things going on. There's a lot of tendrils and sort of leftover explosions and materials that have been lit up by some of that explosive behavior. But at the very center of some of these explosions, you see some really weird kind of buzzing and humming and a star that pulsates really rapidly. Call these things pulsars. And the explanation there is just as stars that are about the size of our sun can collapse into white dwarfs, much more massive stars, when they explode, leave behind even more dense objects called neutron stars. These things are about the size of cities, 10 kilometers in radius, but can be as massive as our own sun. These are actually the things I end up studying most of the time. And these neutron stars will beam out a tremendous amount of radiation and whip around very rapidly. And this is what we see as the pulsation. You can see what the size of a neutron star is compared to some city on Earth, for example. Even larger stars will bypass the neutron star phase at the end of their lives and go straight to a black hole. Some of the more interesting things that people think about when they think about astronomy and astrophysics. We know that black holes exist. We've seen lots of evidence for them. And one of the ways to produce them is in these dramatic supernova events, when the leftover material collapses in on itself and the gravity becomes so great that light itself cannot escape. So I hope you enjoyed our tour of different kinds of stars, remnants of stars, things that stars can produce. Our goal is to be thinking about the planets that are around them. So hopefully this gave you some understanding of the stars, and now it's on to studying their planets.